Hello everybody, welcome back to the CCNA routing and switching video series brought to you by ABY Design and Tech. In this video, we will be having a deep dive look at the Ethernet protocol, and we will be looking at what the Ethernet protocol is and how it allows for data link or layer 2 communication within the same network. So to begin with, what is Ethernet? The Ethernet is a protocol and it operates at layer 1 and layer 2 of the OSI model. I know what you're thinking from my previous video, but you said it only operates at layer 2. Well, for data link communication, so to allow communication on the same network, it operates on layer 2 of the OSI model, and it performs all the functions which are required by a data link protocol. However, Ethernet also defines cabling standards like copper cables, fiber cables, how they work, to allow you to connect your devices together, because it's all well and good defining a set of rules to allow communication, but you still have to define the physical standards or the physical cabling of how the devices are going to be connecting together. And like I said before in my previous video, Ethernet just defines how two devices on the same network can communicate with each other. And Ethernet, it adds what we call a frame to the IP data. So to the data that we're going to send, it adds a Ethernet frame. Ethernet frame has an Ethernet header and an Ethernet trailer. And this frame is used to add data, the relevant information to the data, to allow the data to go from point A to point B over the same network. So as an example, if I want to browse out to the internet, the Ethernet frame and header is what's going to add the correct information to send my data all the way to my router, and then it's going to be the IP information which will tell my router, this guy doesn't want to actually talk with me, he wants to talk with youtube.com, so now I'm going to send this data to my ISP router, etc. So in this video, we'll be having a look at the layer 2 aspects of the Ethernet protocol. So Ethernet defines the use of MAC addresses. Okay, all a MAC address is a physical address that is assigned to a network interface card when that network interface card is manufactured. So if your computer, let's say you have a server, a laptop, or whatever, if your computer has got 4 network interface cards, it's going to have 4 separate MAC addresses. As an example, my laptop has got a wireless network interface card and a Ethernet network interface card. They're both going to have 2 separate MAC addresses. And the MAC address is what we call a physical address because it's bound to that machine. No matter what you do, you can't change the MAC address. You can spoof somebody else's MAC address through software, but you can't actually change the MAC address assigned to that network interface card. Even if I was to take my laptop into work, the MAC address will still be the same. And because of this, it means that no 2 network interface cards can have the same MAC address. The MAC address is 48 bits in length, and it's in hexadecimal format. Okay, so it consists of 12 hexadecimal digits, and each digit can have a value between 1 through 9 or A through F. For example, decimal 1 can be represented by hex 1, but decimal 10 would be represented by hex A. Sorry. Now, breaking down the MAC address, we can break it into 2 halves. Okay, so obviously we know that we've got 12 hexadecimal digits. The first 6 hexadecimal digits, they represent the manufacturer of the NIC card. So the actual company, Intel, Cisco, HP, who actually manufactured this NIC card. Okay, now the last 6 digits, they are used to represent that specific NIC card within that manufacturer. Okay, and a organization called the IEEE, these are the guys that assign the first 6 digits to the different manufacturers. So as example, they're the ones who would have told Cisco that any network interface card you manufacture has to begin with the first 6 digits of CC46D6, or HP, any network interface card you make has to begin with the first 6 digits of 3CD92B. Now, all MAC addresses are going to be 12 hexadecimal digits. However, we can represent MAC addresses in different formats depending on the manufacturer. As example, Windows presents MAC addresses in a different format to Cisco, but essentially they will both have 12 hexadecimal digits. As example, we can represent 3 sets of 4 hexadecimal digits represented by a period or a dot, or we can go for 6 sets of 2 hexadecimal digits, either separated by a colon or by a dash line. Now again, it's just depending on the vendor, on the manufacturer, or sometimes even on the operating system about how these MAC addresses are presented and the format that they are presented in. But it's important to know they can present it in one of three formats. So let's look at how MAC addresses allow for effective communication to take place within the same network. So in this case, Rick wants to communicate with Jack. He's like, okay, I want to communicate with Jack. I want to send him some information. I want to send him some frames, man. So he's going to look at Jack's IP address and realize, and we'll talk about this later on, that Jack is in the same network as me, so I can reach him directly. Okay, let me look at my ARP table to find the MAC address of Jack. So Rick looks in his MAC address table. He knows, oh, okay, his ARP table, sorry, not the MAC address table, the ARP table. That's my mistake. In the ARP table, it will say the IP address of 192.168.1.11 has, or is bound to, or has got the MAC address 0500 6A 5C 6A 7B. So now this file that Rick wants to share with Jack is going to have the source IP address, destination IP address of obviously Rick's IP and Jack's IP. It's going to have the source MAC of Rick's MAC address and the destination MAC of Jack's MAC address. And so even though we don't actually need the MAC address to be able to communicate within the same network, we still travel down the whole OSI model. So we're still going to add all the information at each layer to that data. In this case, Rick sends this file that he wants to transfer over to Jack, and it's received by the switch. Okay, the switch receives, okay, I have received this piece of data, or this frame. So it only sees it as a frame. It doesn't know what the actual data is. It says, I received this frame from Rick. Okay, Rick wants, this frame is destined for 0500 6A 5C 6A 7B. Let me look at my MAC address table. I can see, okay, I have an entry and I know that I can use NFA's fast Ethernet 0/3 to reach Jack. So now I'm just going to send that information or that frame out fast Ethernet 0/3, and now Jack receives that frame. It's going to de-encapsulate, it's going to remove the Ethernet header, the IP header, TCP header, and it's going to pass the information over to the correct software application, and that's going to process that piece of data. Now, when we talk about layer 2, there are different types of MAC addresses. So we have Unicast, which is 1-to-1. So Unicast addresses are only meant for a single device. So like in our example, a Unicast MAC address means that this frame is only going to be sent to one device. Okay, and this, with Ethernet communication, the source MAC address is always a Unicast. In this case, in this example, where the computer on the left wants to communicate with the computer on the right, both the source and destination are going to be Unicast because this frame is only meant for one computer. The next type of MAC address we have is going to be multicast, and this is one-to-many or one-to-a-group. And this MAC address allows us to send one frame to many devices. And so the way it works is that devices will join a multicast group that has been assigned a specific multicast MAC address. And essentially devices will listen in for any traffic that is sent to that specific MAC address. And any traffic that they receive with that multicast MAC address, they are going to process. Think of it like this. Think of it as radio broadcasting. So with radio broadcasting, obviously radio towers are going to transmit at certain frequencies, so different radio stations will use different frequencies to transmit their radio signals, etc. Okay, when you turn on your stereo in your car, it's only going to essentially output, or let's say blast out the radio signals from the radio station that you're tuned into. So depending on the frequency that you're tuned into will depend on what radio station you're listening to. Your radio in your car is still receiving the radio signals or the radio frequency signals from the other radio stations, but it just ignores them because that's not the one that it is tuning into. It's the same thing as with multicast addresses. The only computers that are going to process traffic sent to a multicast address are the computers which are listening in on the multicast address. So imagine this, they've got the error on the wire. Like if I receive anything from, let's say 0180C2 000001, that's a multicast group that I'm a part of. I'm going to process that request. In this example, the two computers on the right, they're listening in on the specific multicast address, so they're going to process the traffic. The computer on the right, the third computer, sorry, on the right, the one that didn't receive anything, he would have actually received that frame, but he's not going to process it because he's not listening in on the multicast group. And the multicast address is always going to be set as the destination if we are going to use multicast. Like I said, Unicast is always set as the source because it's being sent from one device. But we can tell if a frame is a multicast frame if it's destined for a group of computers. If the destination MAC address is in the range of 0180C2000000 through 0180C2FFFFFF, if the destination multicast address is within that range, we know that that frame is a multicast frame and it's going to be sent to a group of devices. Now we have broadcast. Now broadcast frames are one-to-all. This allows a device to send one frame, and that frame is replicated and sent to all the devices on the network. And this is useful for protocols like ARP, Address Resolution Protocol. If you don't know what that is, I have a previous video which you guys can look at. And the broadcast MAC address is always set to FFFFFFFFFFF. It's set to all Fs, and essentially the last usable MAC address. And just so you know, no device will ever be assigned, no network interface card will ever be assigned this MAC address. This is reserved specifically for broadcast traffic. The same as this range of addresses for multicast is reserved for multicast addresses, so no network interface card will be assigned that MAC address. Network interface cards are going to be assigned MAC addresses outside of these ranges, and they will be assigned Unicast MAC addresses. So now let's look at the Ethernet frame format. So like I said, is that Ethernet is going to add what we call a Ethernet header and an Ethernet trailer. A frame, this is referred to as frame, it's going to add an Ethernet frame to the data so that we can get the data from point A to point B within our network. And so this is what Ethernet frame looks like. It's made up of a header and trailer. The preamble is 7 bytes. So the preamble essentially identifies to the receiving device that this is the beginning of an Ethernet frame. Okay, now when the preamble is made up of 7 bytes, okay, so that's it's 8 bits for each byte. Essentially each byte is a pattern of ones and zeros, okay. So 10 10 10 10, and it's used for bit synchronization. So it's used so that both sides can then synchronize themselves, and so that the receiving device is ready to receive this data. It knows, okay, I'm about to receive a Ethernet frame, I better get my act together. Then we have the SFD, which is 1 byte, and that identifies that the next byte of data you're about to receive is going to be the start of the destination MAC address. Okay, now that we have synchronized, I know you're going to send, I'm ready to receive, I know the next byte after this one that I'm going to receive is going to be the destination MAC address, essentially the start of the Ethernet frame. And it's 1 byte in length, and in binary its value is always 1010111. Then we have the type field. The type field identifies that behind this Ethernet frame, so you have to remember that as we're encapsulating data, we're adding a transport header layer to it, then we're putting a IP header in front of it, and then we're putting an Ethernet header and trailer in front of that. So the type field just identifies that what the network layer protocol is behind this Ethernet header and Ethernet trailer, behind this Ethernet frame, and usually this is going to be IP. And CRC, which is known as a cyclical redundancy check, is a 32-bit hash code of data, and it's used to check for data corruption. So the way it works, okay, is that before a device will send the Ethernet frame, it's going to take all the information from that Ethernet frame, the data, think preamble, SFD, destination address, source address, type, etc. It's going to run that through some sort of mathematical algorithm, which spits out a 32 hash code, and it's going to attach that to the Ethernet trailer as the CRC. This is used to check for errors as the data travels. Once the receiving device receives the Ethernet frame, it's going to do the exact same thing. It's going to take that data, the Ethernet header, run that through a mathematical algorithm, spits out a 32-bit hash. If the hash that it's calculated is the same as the hash in the CRC field, it'll know that this frame has not been changed or corrupted during transit. If it is, it's going to drop that frame and request the sender resend that frame again. Now let's actually have a look at what a Ethernet frame looks like in a protocol called in an application called Wireshark. Wireshark is what we call a protocol analyzer. Essentially allows us to capture traffic and be able to analyze that traffic. So as you can see, we have the Ethernet header and Ethernet trailer here. So you can see Ethernet headers here. We have, let's say, the destination address, where this frame is going to, source address. And as you can see here, it lists Dell because it knows these first 6 hex digits have been assigned to the Dell manufacturer. So Dell manufactures this NIC card, or the source, Juniper, manufactures this NIC card. Then we have the protocol, or the type of protocol which is above. So the network layer protocol in this case is going to be ARP. So we're using the ARP protocol. Which is that's going to be the network layer protocol behind the Ethernet header and trailer. And then we have the trailer here, and then in this case, in this example, this is the image I got from Google. We have a frame check sequence, and as you can see is that there's been some sort of data corruption during transit, as the CRC that the receiving device has calculated is different to the CRC the sending device calculates. So next we're going to talk about a very important feature of Ethernet based networks called CCNA CD. This is carrier sense multiple access with collision detection. So before we even had Ethernet switches, we had, this is going back 20-30 years ago, we don't use these devices now, and if we did, they would destroy our networks, because they are so rubbish. We used to use these devices called hubs. Now hubs operated around layer 1, layer 2 of the OSI model. Okay, in my previous video I may have made a mistake. Hubs operate at layer 1. They're essentially physical devices. All they do is just repeat electrical signals. Now that means is that even if one device wanted to communicate with only a single device on the other end, the data that single device sends is going to be repeated and transmitted out every single port on that hub to all the devices which connect to that hub. So all the devices are going to be able to are going to receive the traffic. Again, that's a security risk, but it's also we're using up unnecessary amounts of bandwidth to actually send and receive data. And with hubs, we've got something called collisions. So before we talk about collisions, let's have a look at what a collision domain is. So a collision domain is defined as a shared medium, whereby if 2 devices transmitted at the same time, a collision would occur. So let's look about in a practical sense. And to be fair with me, it always makes sense for collisions if I use pictures. So in this example, the way the hub works on the left is that, let's say that this computer on the left wants to communicate with the top computer on the right. Now, even though it only wants to communicate with that one computer, the way that hub works, the hub's going to replicate that frame at every single one of its ports. Now, with a hub, the bandwidth is going to be shared. So in this case, if it's a 100 megabit per second hub, that bandwidth is going to be shared between, let's say, 4 devices. They're each going to get 25 megabits per second each, and only one device can send at a time. So in this case, if the computer on the device is sending data, the computers on the right have to wait before they send data. They cannot send at the same time. Now, a collision occurs in this case if the computer on the left and the computer on the right, if they both want to send data at the same time, they both want to send a frame at the same time, that's when a collision occurs, because essentially a hub represents one collision domain. Because a hub is such a dumb device, it can't, let's say, control frames. So by control frames, it means it can't hold frames in memory and then send one frame at a time whilst holding the other, or buffer frames, etc. A collision occurs, so computer on the left, computer on the right, they both send data, send frames at the same time. Collision occurs, that traffic is those frames are dropped, then both sides have to back away for a random amount of time before they attempt to resend again. And as you can see, with devices and computers always trying to communicate, collisions in hub type networks happened a lot, and they caused for a lot of issues in network performance as well. So again, hubs were a shared medium and they operated in half duplex. Okay, that means that because the devices all had to share the bandwidth, they could only send at a single time, because they were sharing that bandwidth. Okay, they didn't have dedicated bandwidth. They weren't dedicated 100 megabits per second. They were sharing that 100 megabits per second. They were sharing that wire essentially. And devices connected to a hub need to share the network bandwidth offered by the hub. Only one device could send at a time, unfortunately. And again, if there was a collision, then both devices would back off for random time and attempt to send again. Now, modern Ethernet switches resolve this issue, as each port has its own dedicated bandwidth, that each port is its own collision domain, and each port operates in full duplex. So hubs operate in half duplex because only one device can send or receive at a time. Switches operate in full duplex because each port of a switch has its own dedicated bandwidth. Each port is its own collision domain, and that means that we can have all the devices which connect to a switch being able to send and receive at the same time. Okay, so this shows the difference between a hub and a switch. As you can see, the hub, only one device can send at a time, so either only I can send or only I can send. With a switch, we can all send at the same time, and there won't be any issues because each port represents its own collision domain. Each port has its own dedicated amount of bandwidth. These devices are not sharing bandwidth. They're each, let's say, dedicated 100 megabits per second of bandwidth which they can use. Now let's talk about the broadcast domain, another important concept with Ethernet. The broadcast domain essentially is defined as all devices in the same network are in the same broadcast domain. And earlier we talked about broadcast message. So a broadcast message is if we were to send a broadcast frame, that broadcast frame is going to be able to reach all the devices on that network. So the broadcast domain is defined as if one device were to send a broadcast message, to what other devices will that broadcast message reach? That is the broadcast domain. So as example, because all these devices are in the same network, this whole area represents the broadcast domain. And as you can see, the blue represents the collision domain. So as you can see on the switch, the blue is going to be each port. Now as you can see down here, we have a hub. So that whole area represents the collision domain. So these two devices which connect off the hub, only one of them can send at a time because that's a shared medium. The ports on the switches, they are each their own collision domain, okay? And this whole area is the broadcast domain, because if this computer on the left were to send a broadcast message, all of these computers over here are going to receive that broadcast message, and that is defined as the broadcast domain. And to be fair, that's all there is to it. That's all there is to the Ethernet protocol. So we looked at the layer 2 aspects. In the next video, please join me. We'll be discussing the layer 1 aspects of the Ethernet protocol, cabling standards, fiber standards, etc. Like I always say, please share this video. If you like to see more content like this, please subscribe to my channel. And at the moment I'm covering the CCNA course. If you want to see other courses, then please recommend those to me as well. Again, share this video with other people so we can get high quality free network training to the masses free of charge. Thank you very much.